I'm going to talk about the relationship between Alfvén waves and discrete auroral art. I'll concentrate on a phenomena known as field line resonance, a process in which a global compressional wave propagating in the magnetosphere has a nearly monochromatic frequency. When this wave reaches a closed geomagnetic field line and its frequency matches the natural frequency of that field line, you have a resonance take place in which the global compressional wave transfers energy locally to the field line oscillation, which grows in amplitude and drives a field line current into the ionosphere that can energize ions and electrons. Some of these electrons reach energies sufficient to cause aurora. Because these excited waves are localized in latitude, you get discrete aurora, in this case oscillating at the same frequency as the field line resonance, typically frequencies in the range of a few millihertz. I'm from the University of Alberta, so this is central part of the campus. That's my office, and my colleague Ian Mann is right next door. It's a top 100 university known for its extensive research in the health and sciences sector. It houses around 39,000 students, which corresponds to the second highest student population in Canada. My city is latitudes that are far enough north that you can see aurora. Jielu from Shandong University took this movie of the aurora. You can hear his friends reacting to what's going on above them in the sky. You might see a few trees in a little bit. It's not the greatest resolution, but it indicates what a beautiful natural phenomena the aurora is. Here are the trees. You can see some of the lights of the city. That's a different image, not the one he took. We're interested in the aurora in Canada for a variety of reasons, not least of which is space weather effects on satellites and power utilities that we have across Canada, which encompasses the auroral zone. I'm going to talk about aurora that's oscillating at the frequency of toroidal mode Alfvén waves. As I mentioned, you can have resonant mode conversion from global compressional waves to an MHD plasma wave known as a toroidal mode, which fits into this classification of ULF waves that you can see in this table. I'm talking about waves in the PC5 range. The period of these waves is hundreds of seconds, typically up to, in fact, 1,000 or more seconds. But the bulk of these waves lie in the range of about 2 to 7 millihertz at the range of latitude where you observe them. These PC5 ULF waves, they've been studied extensively for over 50 years. I've listed some of the early papers here. There's a question about how these waves are excited and where they come from. There's some evidence that these waves may actually be present in the solar wind at frequencies that are similar to those found in the magnetosphere. That's not conclusive, but there is some evidence for that. Another possibility is that these waves are excited at the boundaries of the magnetosphere, at the magnetopause, where you have shear flows that drive Kelvin-Helmholtz instabilities and MHD compressional waves. So either surface waves or compressional waves that generated directly on the magnetopause by the solar wind may be the source for these excited waves in the PC5 range. This phenomenon, known as field line resonance, is one in which you form a standing wave on geomagnetic field lines. These standing waves are nearly monochromatic, with frequencies that match the compressional waves in the magnetosphere that are driving them. This is a resonant process in which the excited waves can grow to large amplitude. This is a pathway for energy to flow over vast distances from the outer to the inner magnetosphere and ionosphere, not only field line resonances, but ULF waves in general are observed by missions such as the Van Allen probes and have been identified as a source of high energy killer electrons that can damage spacecraft. There's also some evidence that these field line resonance, these localized in latitude waves, have strong field line currents that potentially act as a trigger for the substormic expansive phase. We're interested in these waves for these reasons, but also because they're ubiquitous and there have various applications. For example, they can be used to infer equatorial region mass densities, which is important for space weather. And because these waves carry field line currents and have both parallel and perpendicular electric fields, they participate in magnetosphere coupling. One manifestation of this is so-called red line emissions at 6,300 angstroms. Auroral arcs, basically, that glow with emissions produced at a wavelength of 6,300 angstroms. There are actually two types of field line resonances. I mentioned only the toroidal mode. There's another mode called the poloidal mode that's no less important, but for the purposes of this talk, the toroidal mode is of interest because the toroidal mode carries a field line current which can drive charged particles along field lines. If these particles precipitate with high enough energy, they can cause the atmosphere to glow as an auroral arc. In the toroidal mode, the magnetic field lines are bending. They're being twisted back and forth in the azimuthal direction as a result of field line tension. They have an azimuthal wavelength that's very long. M equals 0 would correspond to an infinite wavelength at a given L shell. Here, RE is Earth radius. Or they can have M numbers of a few. So M equals 0 is not uncommon. M equals 1 up to 4, 5 is also not uncommon. The poloidal mode, on the other hand, it's referred to as a breathing mode. The azimuthal wave number is large. In that case, the field lines oscillate back and forth in a meridian plane, and at these wave numbers, the waves are localized in latitude, but they don't have an associated field line current. The observed M values range from 0 to hundreds, and the toroidal mode is important in this context because it has a field line current. Here's a toroidal mode field line resonance. This is a solution to the MHD wave equations in which the M equals 0 mode is shown. These are field lines on a particular L shell where the wave is excited. You can see that whatever the excitation mechanism is, we just drive it here with a particular frequency. You get these torsional waves. And so this is an example of a toroidal mode field line resonance. If you move towards and away from the Earth, you'll see that the amplitude drops off in both directions. This corresponds to a localized excitation of a particular wave, the toroidal mode, that will drive field line currents and precipitation into the ionospheres. Here's the geometry of a field line resonance. I've drawn a particular field line. If you look at the plasma flow velocity in the field line resonance, the resonant field line is where the amplitude peaks, and the flow is azimuthal in one direction as you move earthward, and it's azimuthal in the other direction as you move away from the Earth. This velocity field has shear within it. There's an associated radial electric field, and although not shown, there would be an azimuthal magnetic field. So the toroidal mode field line resonance, in which perhaps the wave is being excited by an instability at the magnetopause, it is associated with a radial electric field an azimuthal flow velocity, azimuthal magnetic field, and a field-aligned current. Because it's oscillatory, these field-aligned currents, which maximize near the ionosphere, will be oscillating up and down. Now, I've drawn in just schematically, it's hard to see, potentials corresponding to the electric field. The electric field is perpendicular as you move along the field line, but as you get to lower altitude, you start to form a parallel electric field, not just a perpendicular electric field. These perpendicular electric fields are polarization current in the wave. The parallel electric field, if it forms, must be related to the parallel current through Ohm's law or equivalent. A major challenge is to derive the relationship between this current and the parallel electric field. I'm not going to concentrate on it in this lecture. I will just say that whatever that relationship is, it must be sufficient to drive auroral arcs because of the shear flow that exists across the resonant field line. It may drive Kelvin-Helmholtz instabilities within the arc itself. What I'm showing here is the density perturbation associated with the field line resonance. You're not seeing the waves, you're seeing how the plasma responds to the wave. Plasma is flowing outward and building up in the equatorial plane and creating a density cavity at lower altitudes. These density cavities are a common feature of discrete arcs. So you get this density cavity naturally through the formation of a field line resonance. This is an all-sky camera image of an auroral arc that is actually oscillating in time. The arc starts to wrap during part of the wave cycle, but it doesn't go all the way, so to speak. It stalls out, and so this is like a pseudo breakup. It doesn't go nuts, so to speak, and drive all sorts of auroral activity. The solar wind flowing across the boundaries of the magnetosphere drives surface mode waves, which decay evanescently into the magnetosphere. These surface waves have a certain frequency. When that frequency matches the natural frequency of some field line, you get resonant growth of these toroidal mode waves. What you find is that there's a polarization reversal across noon. Here the polarization is left-handed, here the polarization is right-handed. There's some good and bad aspects of this picture. The good is that it explains why you have toroidal modes, because the source has relatively low azimuthal wave number or phase variations. You stagnate the flow here, but it speeds up along the flanks. So these waves would be expected to be strongest near the flanks, which is what is observed. However, there's no particular reason why the waves should have discrete frequencies, which is necessary to explain why the resonances themselves have discrete frequencies. And also, there are times where you observe not just one FLR of a particular frequency, but more than one. It doesn't explain why you typically observe particular multiple discrete frequency resonances. Also, in the inner magnetosphere, you commonly see waves with frequencies around millihertz, and that would require, if you're talking about a dipole field, very high densities because of the large magnetic field strength in the inner compared to the outer magnetosphere. This mechanism doesn't directly explain why you see very low frequencies on field lines that are at L equals 6 or 7. One would expect much higher frequencies, assuming the magnetic field is a dipole. Here's what Sampson observed without necessarily having this picture in mind. He plotted the polarization as a function of geomagnetic latitude and local time. You can see the polarization reversal across noon. These waves, they exist over quite a range of latitude, and if you pick any particular local time and look at how the polarization changes with latitude. You change from this polarization to the opposite and then back to this polarization. That's what led Southwood and others to come up with this picture and put some theory around it. This is the geometry for two different MHD plasma waves, the shear wave and the fast mode. There's also the slow wave, but we'll ignore that. I'll let you look at the geometry. The difference I want to point out is that in the case of the toroidal mode, there's a parallel current along B. There's a simple dispersion relation in which the wave frequency is the parallel wave number times the alpha end speed. If you excite the wave locally, it's guided preferentially along the magnetic field, and the Poynting vector across the field, the net Poynting vector, is 0. So there's a parallel Poynting flux. In the fast mode, the compressional mode, of course it's compressible. Rather than propagating mostly along the field, it propagates isotropically along and across the field. For large azimuthal wave numbers, it becomes the guided poloidal mode, which is localized on field lines where this mode is excited. Here, the perpendicular Poynting flux is non-zero, and the wave frequency is related to k rather than just the parallel wave number. What about the mathematics of these waves? Well, in general, we have a curvilinear magnetic field. We'll suppose it's a dipole. If we're looking at the poloidal mode, which is the most complex situation, you have azimuthal electric fields, and across the magnetic field you have an electric field, so both azimuthal and radial if we're in the equatorial plane, and also a component of the wave magnetic field along B. The little e is the big E here. This is a fundamental mode, and this is a second harmonic. This is how the electric field looks along the field line. If we straighten out the field lines and draw the electric field from one ionosphere to the other, this is how the next harmonic would look. The wave magnetic field, on the other hand, has antinode at the ionosphere. This would be the fundamental, and this is the next harmonic. In a dipole field, the wave equations are a little bit more complex. One approximation of this is to straighten out the field lines and have this so-called box model. You have to imagine that the ionospheres are here and here, are at the top and the bottom. As you move out towards this is the magnetopause boundary. This would be the earthward boundary of the system, and L would be the length of the magnetic field line. So the magnetic field is straight, but it can vary with the radial coordinate, which is X in this schematic, and along the field line is Z. The X coordinate corresponds to the H component on the ground, which is across the field line from north to south, and the Y coordinate on the ground is azimuthal. The nice thing here is that if you know the density and magnetic field on each of these field lines, you can calculate the natural frequency of a particular field line. And the frequency varies with position because the density and magnetic field varies with position. But at every position, on every field line, you can calculate the frequency through this relation where n indicates either the fundamental or harmonics. So this box model representation has been studied over and over again, going back to Wood and Chen and Hasegawa. Imagine that you have some sort of plane wave propagating in this system. The wave is polarized in the x direction, say. Just like the background field, it can vary with x, but in the other dimensions, everything is periodic along the field, and azimuthally, you have just a specification of wave numbers, k parallel and ky. And here, the frequency of this wave is omega naught. If you solve for the wave, this component Bx, you get an equation like this, and this m number is related to ky, which is the wave number in the azimuthal direction. Because there's a variation in the background parameters with x, there's this parameter here that's related to the gradient in the alpha speed, which is a characteristic inhomogeneity scale length on the resonant field line. So you're looking at some particular place where the field omega naught. On any other field line, so because this describes how the field varies with x, the natural frequency will be something different. Here, omega is the natural frequency, and omega naught is the resonant frequency, the frequency at which the amplitude is growing the most at a particular value of x that we're calling the resonance position. In general, the ionosphere is not a perfect conductor, so this field line eigenfrequency will have both a real part and a damping. If we introduce this parameter epsilon, it's related to the damping rate of the wave frequency, and the inhomogeneity scale length. This equation can be turned into this one. At the resonant field line, x equals xr, and you've got division by the imaginary part here, in which this epsilon may be small. The field can grow to large amplitude on the resonant field line. It's possible to approximate the solutions to that field, that wave perturbation, in the x direction. The equatorial plane, well, in the box model, x is radial. The y component is azimuthal. So the x component varies logarithmically and changes sign across the resonant field line. There's also a y component, which has got this factor here in the denominator. Again, as x goes to xr, you approach the resonant field line, epsilon is small, and you get a large by, whereas bx varies relatively slowly. If you plot these solutions, which are valid in the vicinity of the resonant field line, this parameter epsilon related to the frequency and damping rate, and also the density or the inhomogeneity scale length in the alpha end speed, it peaks on the resonant field line. If epsilon is small, this field goes to very large amplitude, and it becomes more and more localized in x. If you look at the phase, this component has real and imaginary parts. The phase, as you move from one side of the resonance to the other side, the phase changes by 180 degrees. The toroidal y component in this box model dominates the resonant position. The phase of the wave changes sign and becomes almost linear, as you can see on the resonant field line. The sense of polarization determined by the sign of the azimuthal wave number m, and in particular this polarization reverses across the noon meridian. To explain the polarization reversal that is seen, let's forget about the figure on the right here. If we imagine that we have some surface wave excitation on the magnetopause, these surface modes decay in amplitude towards the inner magnetosphere. If they have a particular frequency, where that frequency matches the natural frequency of a geomagnetic field line, you get a large or y component in the box model. There's a change in sign of the amplitude across the resonance. B theta here would correspond to the parallel component of the surface wave magnetic field, but it excites a wave that's largely polarized, has its largest amplitude in the azimuthal component. This is the picture that describes how surface waves at the magnetopause would excite field line resonances, but this is not the only mechanism. As I mentioned, in our box model, keeping in mind that x indicates direction across magnetic field lines, as you move in x, you're effectively changing latitude. And if we look at how the polarization changes of the waves from the magnetopause to the resonant field line and beyond, you can take the wave equations in this box model and write this ratio of Ex and Ey, which is sufficient to define the polarization. And you see it's related to the gradient in the or Y component of the electric field. This is how the electric field varies. You have evanescent decay, resonance, and then decay again. This is how the polarization would change as you move in latitude, which corresponds to what is observed and explained on the basis of the solutions to the wave equations in this box model. What about the optical signature, the auroral signature of these field line resonance? If you think about it, you have this wave localized in latitude, and the fields are all oscillating in time at a particular frequency. This is how the pattern of currents evolves during one cycle of a field line resonance. In one particular phase of the wave, you've got current into the ionosphere, across the ionosphere. These are Peterson currents, and then back out. 90 degrees in the cycle later, the pattern of currents evolves to this. Now you've got field-aligned currents into the ionosphere and out of the ionosphere in this case. Then you evolve to this pattern, but half a cycle or a quarter cycle later. Instead of this being the upward current, this is now the upward current. And then finally, in the next part of the cycle, you're mirroring this one in which the currents are down and then upward on either side of the arc, and then you'll go back to this pattern. The precipitation of electrons is associated with the upward parallel current. In this part, you'll have downward electrons on the southward side of the resonance. Then you'll have the current upwards, poleward of this current. Then it will evolve to this. So you've got upward parallel currents moving from south through the resonant field line to north of the resonant field line and eventually downward. This is a simulation of a field line resonance in a box. This is the equatorial plane. This is halfway to the ionosphere, and this is at or near the ionosphere. What's projected on this plane is the pattern of upward field line current. There's a wave, a compressional wave exciting the field line resonance, and so this direction would be x across the field line. You can see there's a pattern of field-aligned current, and this is the azimuthal direction. If you were sitting at a particular location, this instant you're not seeing upward field-aligned current, but the phase propagation will cause this pattern of motion of the currents. You'd see this pattern of upward current in your field of view if you're looking up with an all-sky camera. Here's an attempt at explaining this. This is an all-sky camera at Rankin Inlet, no relation, in northern Canada. And this red line emission is produced by electrons precipitating within a field line resonance when the current is upward. If you look here, there's a sequence of images spaced a certain interval of time apart. It's easier to follow the maximum current. Here the arc is fading, and then it starts to reform, and then you'll see this pattern of currents move poleward and then fade, and then eventually it'll reform on the southward side, move poleward and intensify, and then fade again. And so you see this pattern of upward field-aligned current that begins at the southward portion of the arc, intensifies as it moves poleward, and then fades with the next cycle coming back into the field of view. Imagine drawing a circle here that represents the all-sky camera, and this is exactly what you would see. How does it look in a time evolution? Here's the all-sky camera at Rankin Inlet with this field of view, but at Rankin Inlet. You can see these moving arcs, that as one arc fades, the other arc comes into the field of view. So that's the phase motion of the wave in the azimuthal direction, projected to the ground in terms of the field-aligned current. If you imagine drawing a line through this arc system, and then you plot the intensity that you see as a function of latitude and time, then this is the picture that you get. In terms of UT, you're looking at a range of latitudes at a particular longitude corresponding to this interval of UT. What you see are these arcs that form and then fade and reform. You'll notice that the angle that the arc makes with the vertical is the slopes are different. The slope is steepest here, and then it's tilting as you move later in time. This is evidence of phase mixing. In this case, the arc is not only oscillating, but its intensity is changing with time. As the intensity increases, the arc narrows in latitude, and that's reflected in the tilting of these phase front in the kilogram, which is taking the intensity as a function of latitude and time. In this case, the frequency is about 1.4, and it's a fairly large high latitude. If it were a dipole field, which it's not, it would be around L is 11.5. This is typical of the apparent phase motion of these arcs, that the phase motion is in the order of a few hundred meters per second. This is how an auroral arc is formed by resonance. A periodic toroidal mode wave with a particular frequency, in this case 1.4 millihertz, is driving auroral arcs with typical scales 15 to 20 kilometers. So what about dipole fields? That's a box model. In a dipole field, this is actually showing the poloidal mode. The toroidal mode, the field lines are twisted in the azimuthal direction, but in the poloidal mode, the field lines are wobbling back and forth in the meridian plane. If you go between the ionospheres, the electric field looks like this, and for the wave magnetic field, it looks like this. You would see this type of motion for the next harmonic. Here it's a half wavelength between one ionosphere and the other. Here it's a full wavelength. So this is an odd mode and an even mode. Although the geometry for the toroidal mode is the same, a dipole, the field lines correspond to a twisting in the azimuthal direction. For the poloidal mode, it's like a breathing in and out of the magnetic shell on which these waves is forming. For sake of completeness, if you take the ideal MHD equations and solve for the various components of the wave, you have an azimuthal electric field in both a cross field and a long field components of B. This is the polarization characteristics of the toroidal mode. Because there's a field aligned component of B, this corresponds to a compression of the magnetic field. If you assume there's no variation in phi, you can write down a wave equation for the poloidal mode azimuthal electric field. This equation can be solved to find the eigenmodes. I'm not going to go into that today. For the toroidal mode, you can do likewise, but the toroidal mode, it has an azimuthal component of the wave magnetic field and a cross field component of the electric field. If we're talking about ideal MHD, there's no parallel component. The field lines are moving in the azimuthal direction without changing the magnitude of B. From E cross B, you can see that the Poynting flux is along the magnetic field. These waves are not only driving field-aligned current into the ionosphere and out of the ionosphere, they're transferring electromagnetic energy along the field line into the ionosphere. There are lots of satellite observations showing evidence of large parallel Poynting flux associated with alpha N waves. These Poynting fluxes seem to be strongly dissipated as the waves propagate to the ionosphere. The dissipation of this parallel Poynting flux is going into particle motion parallel to the magnetic field. When that occurs, you've got a relationship then between the field line currents and this Poynting flux, and hence there's a relationship between parallel Poynting flux and the aurora. Again, there's a wave equation for this that I won't solve. Okay, why are you showing these equations? Well, I just want to point out that there are, in general, two modes of excitation. One is the poloidal mode, the other is the toroidal mode, and normally the coupling between these different wave modes is neglected. The limits in which that is justified correspond to m equals 0 for the toroidal mode and m equals infinity for the poloidal mode. In those two limits, the wave modes are uncoupled, but anything in between, there's a coupling between the toroidal and the poloidal mode, and it has to be accounted for. In general, when you solve the wave equations, there are two types of solution. In the uncoupled case, you can refer to these two solutions as toroidal and colloidal. In the case where you can't decouple them, there are still two solutions, but they don't fall into the category of toroidal and colloidal. We refer to them as mode 1 and mode 2. Mode 2 in the appropriate limit would correspond to the toroidal mode. But in general, in an arbitrary magnetic topology, you don't have this delineation where you can refer to one wave as toroidal and one wave to colloidal. So what we're showing here are field lines that are non-dipolar. They're oscillating at their natural frequencies. The amplitude at which they're oscillating is matched to what a satellite is observing, or two satellites actually, is observing as the satellites propagate along this trajectory. There's two objects here that correspond to two of the famous satellites that measured the amplitude and polarization of waves excited in this magnetic topology. Of course, the waves in the outer magnetosphere are lower frequency than the waves in the inner magnetosphere. The model doesn't give you directly the relative amplitude of waves on different field lines. That has to be obtained from measurement. In this case, the Themis spacecraft, two of them measured the amplitude and phase or polarization as a function of time. That's what's shown in the bottom. These are spectra from observations of these waves by two of the Themis satellites. Here you can see the trajectory. I think this is a Themis D as it moves from the inner to the outer magnetosphere. So you can see that there's a frequency variation. There are no discrete peaks in this case, which might suggest that the source of excitation is the Kelvin-Helmholtz instability, which has no reason to be monochromatic. The surface waves have a reasonably wide spectrum and couple through all the field lines and drive them at their natural frequencies. What I want to point out is that these alpha waves that are being excited either through Kelvin-Helmholtz instabilities at the magnetopause or through some other process don't just drive waves at discrete frequencies. In general, they drive a continuum of wave frequencies corresponding to the natural frequencies of different field lines. Again, this is a trajectory of the Themis satellites for a case that was analyzed by Saris in 2009. Here you've got the radial electric field, and this is the frequency for the electric field oscillations as seen by Themis D. This is the electric field seen by Themis D. Oh, this is the radial electric field. I was getting myself confused. And this is the azimuthal electric field. Basically, the spectra that are following these black and white lines are the same for both the azimuthal and the radial components of the electric field. The black and white lines indicate the two solutions to the wave equation, where neither of these solutions can be characterized as fully toroidal or fully colloidal. Nevertheless, one of these solutions corresponds more to the toroidal than it does the colloidal. The fundamental and first harmonic that are shown here, the mode that most closely matches the toroidal mode, fits the spectra of the oscillations, whereas the other mode, which more would correspond to the colloidal mode in terms of its fundamental harmonic, does not. It suggests that if the Kelvin-Helmholtz instability is exciting these waves, they're exciting mostly the toroidal mode, consistent with how the density and alpha and velocity vary throughout the magnetosphere as you cross magnetic field lines from nearer to the Earth to further from the Earth. In order to get these two solutions, this is a bit of a long story, the background magnetic topology has to be specified along with a profile for the plasma density. This is the density profile that was used, or the alpha n speed profile, which when you put it together with the background magnetic field and solve for the two wave modes, one being more toroidal-like and the other being more poloidal-like, is used to fit the spectra. The fitting is best for the toroidal mode. The optical signature of field line resonance can also be determined from meridian scanning photometers. These meridian scanning photometers, they look at particle precipitation by scanning back and forth in time across a range of latitude. From these scans, you can construct this type of plot, which is the intensity of the emissions that the meridian scanning photometer is tuned to. By sampling the precipitation and ordering it by wavelength, you can construct these pictures. You're looking at emissions caused by particles of a certain energy that cause 5577 angstroms emissions. H beta corresponds to precipitating protons for the most part. Then you have another wavelength, and then 6300 angstrom emissions. The MSPs sample precipitation in different energy ranges. 5577 is produced by higher energy electrons, several keV, but 6300 is predominant. Here's an example. I showed something like this earlier, but it was obtained from an all-sky camera. In this case, we have meridian scanning photometer at Rankin Inlet, and it's sampling emissions from precipitating electrons that are exciting the 5577 angstroms line. You can see this pattern that you saw in the earlier all-sky imager data, this tilting pattern of the emissions, which in this case are produced by energetic electrons. This is the frequency spectra, and this is the amplitude. There are two peaks. One is at around 2 millihertz, and there's another peak at around 2.5 millihertz. Here we have a situation in which we have aurora being produced by two waves of different frequency, somewhat overlapping. If you focus on the 2.5 millihertz, well, if you look at how amplitude and phase vary with latitude, in this case, there is in fact a peak around 72.5. The phase changes by 180 degrees, but there's actually two resonances here. One has smaller amplitude than the other. They're somewhat interfering with each other. But from the MSPs, you get the same information as you do from magnetometers and all-sky cameras, which is that you can construct the amplitude and phase from measurements of the particle precipitation causing emissions at a particular wavelength. This is another example. Now we're looking at latitudes corresponding to roughly geosynchronous orbit. There's some magnetometers in Canada. One is at Gillam, the other is Fort Churchill Island Lake. These are just three of many. In the magnetometer data, you're seeing a wave that is peaking at latitude of Gillam, which is roughly geosynchronous, and then the amplitude drops off as you move northward and southward of Gillam. If you take the magnetometers and look at the power spectra, you've got a peak at around 1.3 millihertz. This is on field lines that are roughly, if the field is dipolar, this would map to geosynchronous orbit, roughly. One wouldn't expect a wave to have that lower frequency at L of 6.7. So this is an anomalously low frequency field line resonance for the latitude at which it's observed. But again, if you look at all-sky camera images, you see this periodic reforming arc pattern. In this case, it's in the red line. Most of the intensity is in the red line emission, which is indicating hundreds of EV electrons that are produced under this field line resonance, causing again a discrete arc. What I want to point out is that for L of 6.7, this low frequency is problematic because the magnetic field is strong. To get that frequency, if the field is dipolar, one needs much higher densities in the field line than one would expect. Another interesting aspect is how the phase varies with latitude across this resonance. It's much larger than 180 degrees. It's not what you'd call a classic type of field line resonance. It has an anomalously low frequency, and the phase difference across it is much larger than 180 degrees. That can occur if you're reaching small perpendicular scales at which electron inertia effect become important. When the resonance is narrow, you trigger dispersion within the waves, and this dispersion causes a transport of wave energy out of the resonant field line, which is not associated with the MHD torsional alpha wave. The anomalously low frequency, even though we're at L of 6.7 on the night side, suggests that the field is not dipolar, that this field line is stretched into the night side central plasma sheet, and as you lengthen the field line, you lower its frequency. The 4861 emissions in this case indicate precipitating energetic protons. This band of precipitating protons is caused by pitch angle scattering on non-dipole field lines on the night side. The field line curvature is much smaller when you have stretched field lines. In that situation, you have curvature scattering, giving you this band of proton precipitation spanning this range of longitude. If you look in the 6300 angstrom emissions, you see evidence of the field line resonance, which is near the peak in the emissions produced by pitch angle scatter. So this field line resonance is located in the region of proton precipitation, which is itself an indication of strong tail stretching, even though we're at L equals 6.7 on the night side. This particular dispersive FLR was also seen in a NASA FAST satellite overpass. So we have clear evidence of a dispersive FLR forming on the night side on stretched field lines, which are unstable to substorms, indicating a potential connection between field line resonances and substorms, which is a story for another day.